This is a question about period 3 and the oxides of them. So it's periodicity, but year 13 periodicity. Goes all the way through to G, so try each question, pausing as you go. Once you've come up with answers, review and see how you did. Here's A, B and C. Part D. E, F and G. And that's the end of the question. So let's start going through. A, we want to know the equation for the reaction of phosphorus with an excess of oxygen. So we're going to take our P and our O2, remembering that oxygen is diatomic. You have got to remember that the oxide of phosphorus is P4O10. And what's then left is the balancing. Now I need 5O2 and I need P4. You will get the mark if you put 4P. But you are aware, or need to be aware, that phosphorus exists as P4 because that helps to explain why it has the melting point that it does when we do periodicity back in year 12. Moving on to part B, a test you could carry out in a test tube to distinguish between sodium oxide and the product in part A. So not outlining very clearly what you need, you've got to do a little bit of thinking here to apply your wider knowledge. The first thing you're going to do is dissolve them in water. And once you've done that, you can measure with a pH meter. You could give a named indicator if you wanted to. You'd need to know the right colours for the right places. Now, the reason that we do this is because Na2O would have a pH above 7 and P4O10 would have a pH below 7. And the reason that you would be able to come to that conclusion is that you have got to remember that non-metal oxides are acidic and metal oxides are basic. A really handy way to remember that, sulfur dioxide is a non-metal oxide. It causes acid rain. So you can use that to link together the key ideas that you need. Moving on, state the type of crystal structure in silicon dioxide and sulfur trioxide. So, silicon dioxide is giant covalent. Silicon dioxide often comes up in questions as an application question to show your knowledge of diamond because it has a very similar structure. Sulfur trioxide is molecular covalent, sometimes referred to as simple covalent. Moving on to part D, why does silicon dioxide have a higher melting point than sulfur trioxide? Well, this actually takes you right back to year 12 bonding. You need to know what the bonding is. We've already touched on that in part C, but you then need to be able to articulate why the melting points would be different. So let's take a look. Covalent bonds in the Si2 are broken when we melt it. So we're actually breaking covalent bonds. But in SO3, we don't break the covalent bonds. In any molecular covalent compound, we simply overcome the van der Waals forces. We've got 2 marks. Covalent bonds are stronger than van der Waals forces. That might seem like such a common sense thing, but it's worth putting down. That was a mark in this question. And finally, covalent forces require more energy to be broken. So there's really quite a logical way through there, and it's quite easy to pick up the 4 marks as long as you're confident on the different bonding types. Moving on to E, F and G, here is E, an equation for the reaction of sulfur trioxide with potassium hydroxide solution. This again relies on you knowing that non-metal oxides are acidic. So we're essentially dealing with a neutralization reaction. Now, when I take a look at this and I think about potassium with SO3 or a sulfur oxide, I'm actually going to go to K2SO4, potassium sulfate. I also know that when I neutralize, I'm going to make water. All that is then left is the balancing, and we are done. For F, we write an equation for the reaction of an excess of magnesium oxide with phosphoric acid. Magnesium oxide is a metal oxide, so it's basic. It's another neutralization reaction. MgO reacts with H3PO4. You've got to know that structure. And we're going to make magnesium phosphate, so you'd need to know that PO4 is -3. You can work that out from the 3 plus 1s in the H if you know the phosphoric acid structure, and its neutralisation, so we know we're making water. And then we balance. And finally, draw the display formula of the undissociated acid formed when sulfur dioxide reacts with water. So that would be H2SO3. So then we are looking for this structure.